and welcome back to Cafe con Chemistry. We'll be continuing on with kinetics in this discussion and building further on reaction rates. In this discussion, we will focus on the components of rate laws, including rate constants, reaction order, and half-lives. I mentioned earlier how different factors can affect the reaction, such as temperature and concentration. However, when we have been writing the rates of reaction, we have not yet taken into consideration some of these factors. The rate law, also known as the rate equation, expresses the rate of the reaction with respect to concentration and temperature. We will continue using the following general formula as before, where A and B react to form C and D. A generic rate law is as follows. Rate is equal to K times the concentration of A to the M power times the concentration of B to the N power. If you had additional reactants, you would also include them in this expression. Now let's break down and define each part of the equation. The term K is known as the rate constant and is a proportionality constant that relates the rate of reaction at a specific temperature to the concentration. Note that K is specific to a certain temperature, so changing the temperature will change the value of this constant. The exponents M and N are known as the reaction order, which shows how changes in concentration affect the rate. The overall rate order is equal to the sum of all the reaction orders. Key things to keep in mind are the coefficients in the general reaction, denoted as lowercase a, b, c, and d, are not necessarily related to the rate constant. In order to determine any component within a rate law, such as rate reaction orders and rate constants, they must be determined based on the experimental data. We will be going over 3 reaction orders, but keep in mind these are not the only orders you can have. Reaction order is the relationship between concentrations of species and the rate of the reaction. Some common orders are 0, first, and second order. A first order reaction is denoted when the exponent m is equal to 1 and means that the rate depends only on one reactant. This means if the concentration of A doubles, then the rate doubles because it depends only on A. The rate law would be written as follows. Rate is equal to the rate constant times the concentration of A to the first power. You do not need to write the exponent 1 because it is assumed if not written. In the case of second order reaction, the rate depends on the concentration of 1 second order reactant or 2 first order reactants. Remember, previously I mentioned that the overall rate order is equal to the sum of all the reaction orders. Examples of second order rate laws are as followed. Rate is equal to the rate constant times the concentration of A squared, or the rate is equal to the rate constant times the concentration of A times the concentration of B. In this second case, I did not include the exponent 1 because it is automatically assumed. Zero-order reactions are independent of the reactant concentration. This rate law is as follows. Rate is equal to the rate constant of that reaction. So far, we have only discussed the differential rate law, which looks at the rate of the reaction as a function of concentration over a period of time. However, there is another form which is known as integrated rate law. Integrated rate law describes the reaction order in terms of initial concentration over a period of time and can be derived by setting the rates of expression equal to each other. Here is a figure listing the integrated rate laws along with a graphical representation of 0, first, and second order rates. It is important to note the axis on each graph, so when you are working through problems, you are aware of which rate order you are in respect to. Another component that is displayed on this graphic is half-life equations. The half-life of a reaction is the time it takes for your initial concentration to decrease by half. Let's work through the following problem using an integrated rate law equation. At 1000 degrees Celsius, cyclobutane at 2 molar concentration decomposes in a first-order reaction to 2 molecules of ethene with a rate constant of 87 per second. What is the concentration after 10 milliseconds and how long will it take 70% of cyclobutane to decompose? To approach this problem, we need to identify a few important keywords. The first part of the question informs us that this is a first-order reaction and they want to know the concentration of cyclobutane after 10 milliseconds. which means we need to use the integrated rate law. They also provide us with the rate constant. Let us go ahead and set up the equation and plug in the known values. To solve the concentration after 10 milliseconds, we need to take the inverse of the natural log, which we set everything to the power of e, and this simplifies to the following. Now, we must solve for C4H8 subscript T, so we multiply each side by the initial concentration, and we end up calculating the concentration after 10 milliseconds to be 0.838 moles per liter. The next part of the problem asks how long it would take for 70% of cyclobutane to decompose. We will similarly approach this problem, but instead we'll be solving for time. The first step is to determine the concentration of cyclobutane once it has decomposed 70%. We need to multiply our starting concentration by 30% to determine how much is left. 2 moles per liter times 0.3 is equal to 0.6 moles per liter. Once we have our initial and final concentration, we plug in our known values into the integrated rate law equation and solve for time. We rearrange this equation to solve for time by dividing both sides by the rate constant, and time is equal to 14 milliseconds. I know this lesson we covered a lot of information, but remember you can always go back and rewatch any video if you need to review any topic in particular. We covered different components of rate laws, including rate constants, rate reaction order, as well as half-lives. Thank you for watching and have a wonderful day.